Hey there, folks. Okay, I'm going to go over the lab data with you now that you've seen the two videos, one video of lithium, sodium, and potassium reacting with water, and the second video of, let's see, magnesium, calcium, and aluminum reacting with water. Okay, so just want to explain something. The first video, lithium, sodium, and potassium reacted with water. Lithium fizzed and bubbled with water, and it turned that water and the phenolphthalein pink, and lithium also floated on top of the water. Sodium fizzed quite a bit more vigorously. It was kind of spinning itself into a little sphere as it was reacting and fizzing. It also floated on water, so it had a density of less than 1. It was bubbling and spinning a bit more vigorously than lithium was. And then potassium reacted and fizzed with the water, but it also gave off so much heat that it actually ignited the hydrogen gas that was being produced. All of these produced hydrogen gas, but only potassium was producing enough heat to actually ignite that hydrogen gas in the video that you saw. They all floated on water, they all were less dense than water, and they all turned the phenolphthalein that we put in the water pink. So they all produced a basic solution. All right, so with the same number of valence electrons, these have similar properties. Turning water into a base, making the phenolphthalein turn pink, floating on water, very, very fast reaction with water, producing hydrogen gas in water. So they all had similar properties. But if we look at them, okay, they all have one valence electron, so that's what gives them similar properties. But lithium reacted sort of in the most wimpy way. Sodium reacted a little more strongly, and potassium reacted really strongly and was really the most exothermic of all. So they became more reactive as their radius increased. Why is that? Well, as the valence electron becomes easier to remove when it's further away from the positive nucleus, that means that element is going to be more reactive. If the valence electron is close in with not too much shielding from other layers of electrons, then it's harder to remove that valence electron. So lithium, it's harder to remove that valence electron. Sodium, it's a little bit easier to remove the valence electron. And with potassium, it's even easier to remove the valence electron. And if we were to keep going down this group with rubidium and cesium and francium, they are even more reactive in similar ways, but more and more reactive because it's easier and easier to remove that valence electron when it's further from the nucleus. Okay, in the second video, you saw magnesium, calcium, and aluminum. Aluminum was the shiny stuff that really didn't react at all. Calcium were those crusty little pebbles, and they reacted pretty quickly in water, not quite like lithium, sodium, and potassium. Magnesium just reacted a little bit. So there is another pattern here. Lithium, sodium, and potassium in group 1 all reacted very vigorously with water. Magnesium and calcium reacted a little bit with water, and then aluminum didn't react at all with water. Okay, so let's get the lab data chart filled out and we'll see some patterns. Okay, so in the first video, lithium, sodium, potassium, they react very fast with air. In fact, we have to store them under oil. So that's proof that they react very fast with air. We can't even store them in open air. They reacted very fast. They instantly started to fizz and bubble and spin around when we put them in water. The reactions went from lithium, a little bit exothermic, sodium, a little more exothermic, potassium, really exothermic. It actually ignited the hydrogen gas that was being produced. They all produced gas, but potassium was producing that gas the fastest and was able to ignite it. So the gas was produced very vigorously for all of them, but it actually increased. And so potassium was producing the most gas and was the most exothermic. That's why it was the one that ignited. They all turned phenolphthalein pink, so they all produce a base in water. Okay, now going to the second video, aluminum, magnesium, and calcium. Aluminum basically looks shiny, and so that means it's not really reacting with the air. Magnesium looks a little bit shiny, but it had kind of some speckles on it, so that has a slow reaction with the air. Calcium doesn't even really look like a metal. It looks like crusty little white or gray pebbles. So calcium has a pretty fast reaction with the air. Reaction with water. Aluminum did nothing. The magnesium did react a little bit with the water, and it turned the phenolphthalein pink. We knew something was going on there. by seeing the phenolphthalein turn a little bit pink. But calcium, you could see it fizzing and bubbling, and you could tell it actually was reacting pretty much instantly when we put it in the water. So aluminum had really no reaction at all. Magnesium might have been exothermic, hard to really tell if it felt warm, but the calcium was hot to the touch. That bubbling calcium that turned really pink was hot to the touch. So aluminum and magnesium didn't really produce any gases, but calcium definitely was bubbling and fizzing and producing hydrogen gas, just like lithium, sodium, and potassium. It was, again, aluminum and magnesium not producing any gas, but calcium vigorously producing gas. The aluminum did nothing with the phenolphthalein. The magnesium, again, turned the phenolphthalein a faint pink. That's how we knew it had a little bit of a reaction with the water. But that calcium, man, that stuff turned pink, okay? So you can fill out the rest of this chart using your periodic table. Just want to remind you about that. And so hit pause while you do that. Okay, we're back. Let's sum things up on the second to last page of your lab. So we're talking about just metals here in today's lab. And as we go down a group of metals, the elements become more reactive. Why? That's because valence electrons that are shielded from the nucleus are easier to remove. So as we go and compare, say, something like potassium with 4 shells of electrons to lithium with 2 shells of electrons, the potassium was more reactive. The metals become more reactive as we go down a group because things with more shells of electrons have an easier time giving up an electron, giving up their valence electron. That means they're more reactive towards the bottom of that group. Okay. If we look across a period, though, there's a different trend. Sodium was reactive, but then magnesium was quite a bit less reactive, and aluminum wasn't reactive at all. So as we go across a period, the metal elements become less reactive. And this is basically, it comes down to a simple idea. It's easier to remove a smaller number of valence electrons than a larger number of valence electrons. For example, aluminum has 3 valence electrons. That's harder to remove than sodium, which has 1 valence electron. And that's what it comes down to. So going across, the metals get less reactive. It's easier to remove 1 valence electron. It's harder to remove 3 valence electrons. And I strongly recommend you use this page, this second to last page of your lab, to help you with CER 8.1. Make sure you get that done. It is required. Use this page to help you. Thanks for watching.